Okay, so let's see if it works. It works. I never done this. I've been taped before and put it online, but sometimes I find myself without time to do this. And I thought, well, why not do both things at the same time? So let's see how that goes. So these problems, they cover subject of chapter 19. And we have an exam coming up, right? When is it? It's in the syllabus. Somebody can check that for me. But it's coming up. So and also homework, you should be start, submitting and give it to me. And I think today's the due date, isn't it?
No, it's supposed to be Monday, but
Oh, so it's gonna be Tuesday. Okay. All right. So you guys are on top of chapter 18. Chapter 19 is coming, and so let's try a few exercises and see how they go. So how much kinetic energy? So I have to be smart with these buttons here. How much kinetic energy does a proton gain if it is accelerated with no friction through a potential difference of 1 volt? So there is a potential difference. Let's write the given information. 1 volt. And the proton is this much times heavier than an electron. I read this before. I just wrote down the mass of a proton. We need a mass because of kinetic energy. Kinetic energy has an expression. Kinetic energy has an expression that is half mass of whatever particle you're considering times its speed squared. So V stands for speed, does not stand for voltage. Why am I saying that? Because I've been correcting Phys2B exam for a while, and I'm seeing students that they just look at the cheat sheet and they misplace voltage and speed because they are both symboled with the letter V. So let's see how that goes. So we are talking about energy, and let's pull up the equations or the ideas we explore on Tuesday with respect to voltage, energy, and work, and charge, and force, how all of those relate to one another. So let's start first with force. According to Newton's second law, we learn a lot this in Physics 2A, force is proportional to the acceleration of an object. So by F here is not just one force, but the net force, which means if you add all possible forces that happen to be acting in some particle, then the net force is proportional to the acceleration of that particle. And the proportionality is given by the mass of that particle. Okay, but how does force relate to energy? Well, we learned the concept of work. Work is, for us, a product of force and displacement. Force and displacement. And work is given by a quantity, joules, which is the unit of energy. Okay? Now, when we study Physics 2B, this is pretty much Physics 2A. When we study Physics 2B, we learn about potential, electric force, potential energy, and potential. So potential, V, this quantity V, and that is what we are exploring in chapter 19, is given by the ratio of energy per charge. So which means if you have an electric field in a given environment, imagine you have an environment somewhere like a box, and then you have electric field lines, like those lines you guys work in the lab. So you have electric field lines in space that have a given orientation, and in this box you come with a particle. Oh, what did I do? You come with a particle. What am I doing? Oh, there you go. you come with a particle and you place in that box, in that environment, so this particle will feel a force. And the force, and this we are learning physics to be, the force is equal to the product of charge times the electric field lines, the electric field itself. So QE is the fruit. So that is the force the particle feel. If it is a positive particle, it's going to be moving in the direction because the force will bear the direction of the electric field. If the charge is negative, the force is going to bear a positive direction. So that's the second major equation we are learning in this chapter. So basically, if you look at the problem here, how much kinetic energy does a proton gain? So we are talking about energy. So we are talking about work. We are talking about if the energy is associated with the mobility, and that's the only one. We don't have potential, gravitational potential energy here expressed. Then we are talking about kinetic energy, basically. Okay. Now, what is the energy associated with this electric field? Well, the energy, the work by unit of charge is equal to the voltage, right? So the work, which is energy, so this is energy, is equal to Q times V. Q times V. So the energy is then equal to the charge of a proton, because we are talking about a proton, the charge of a proton, 1.6 10 to minus 19 coulomb, times the voltage, which is this much volts. So the energy we are talking about is 1.6 10 to minus 19 joules. So that's the energy. Now, that's it. What? What? EV, electron volts. This is a unit of 1 electron volts is equal to 1.6 times 10 to minus 19 joules, right? So the proper answer would be, but I don't want you to worry about electron volts because units of energy here is going to be pretty much joules. That's what we saw before. Those of you getting late, get a handout here, but the questions are on the board. So let's try this one. So we have a tiny particle, and the charge is 5. Oh, this I don't know what it is. That came badly copied. Do you have any paper better? Micro? Okay. So the charge, I'm not going to give a big round now. Oh, by the way, in the previous exercise, you have information that you didn't need to use, right? The mass of a proton and blah, blah, blah. All of that was not important. So you have a tiny particle. The charge is positive 5 microcoulomb. And is initially moving with a certain speed. So I'm going to write lowercase v to denote speed, 55 meters per second. And it is accelerated. And this charge is accelerated through a potential difference of 500 volts. So the voltage that is being accelerated is 500. Now, how much kinetic energy does this particle gain during the period of acceleration? So we want to find the energy of this particle. So again, how do we solve for that? What's the basic equations we learn here? We know. So the work, which is energy, is given by Q times V. Or, as we presented before, the definition of voltage is the work that is the electric field exerted on the charge by unit of charge. So no matter which equation you want to use, it's all good, right? They are basically the same equation. So if you want to find the energy, it's pretty much getting the charge that is given and multiply by the voltage. And then we have the work that is exerted on the particle given by the electric field generated by this charge distribution that has a potential difference of 500 volts. So this is the equivalent of 25 times 10 to minus 4 joules. So I'm talking about joules here. That's energy. So how much kinetic energy does this particle gain during the period of acceleration? So look at this. You have a situation, the particle was moving initially with a speed of 55 meters per second. And then it enters a region in which this particle is accelerated by 500 volts, right? So according to the work kinetic energy theorem, this work here that is given to this particle, the work is equal to the change in kinetic energy of that particle. Okay? So this work is going to be given by half mass of that particle, final kinetic energy square, minus half mass of that particle, initial kinetic energy square. But see, if it is being asked how much kinetic energy does this particle gain, so how much more kinetic energy is going to be gained in addition to what it had before, because it had some kinetic energy and it's going to gain something else. So what it gains is pretty much 25 times 10 to minus 4 joules. This is what this particle will be gaining. Does that make sense? And because it gained that energy, its speed is going to be grown by some amount, and you could calculate that if it were asked. Okay. So in other words, the gain in kinetic energy is pretty much 25 10 to minus 4 joules. Does that make sense? Now, if I asked you what's the particle speed after it passes this region that has a 500 volts, if I had asked you that, what would you do? Say it again. It's being taped. Don't forget. Yes. Okay. What would you do? What would you do? Come on.
You scared her?
Okay, so what is the initial kinetic energy? So the work we have, 25 times 10 to minus 4 joules, so we have that. What is the final kinetic energy? Whatever mass the particle has, final speed square minus half mass of the particle and the square of the initial velocity. So if the particle has a mass, and I'm making up, so I'm making up mass because the mass is not given, right? So I don't have the mass of that particle. So if the mass is, let's say, 1 gram, which is 10 to minus 3 kilograms, then I can replace that information in the equation, half times mass, 10 to minus 3 kilograms, final velocity square, which I would like to find, minus this quantity here. Okay? And then the rest is pretty much calculation. So you take this quantity here, you add this quantity to both sides of the equation, and then you cross multiply 2 divided by 10 to minus 3, take square root, and then you have your speed. Thomas, is that okay? You seem to be, what's going on there? So this is not for this problem. Only if I ask you, what is the final velocity once the particle has passed this 500 volts region? So imagine the particle is coming and then enters in that region and then is accelerated. So the speed is going to start growing all the way to the end of this 500 volts. And then I ask, what is the speed at that point? Okay. So again, exactly what did we use? We use this equation, which relates work on the particle done by the field and the voltage and the charge of that particle. Okay? And then you have to remember your concept of energy and kinetic energy or whatnot. Question?
So the answer for the second question is C?
Should be, yeah, 20, let me see, 25 10 to minus 4 is 2.5 10 to minus 3. Yeah, that should be C. Yeah.
So the work is equal kinetic energy?
Yeah. The work done on the particle, because is equal to the change in kinetic energy, is the final minus initial. But what the problem is asking is how much kinetic energy does this particle gain? So what's the excess in kinetic energy? What is the del Ke? But the del Ke is directly given by the work. Right? Is that okay? All right. Now, number 3, if an electron is accelerated from rest through a given potential energy, given potential difference of, not the energy, of 1500 volts, what speed does it reach? So let's see if you can do that. Try to outline the solution to this problem.
When we're writing out problems and like working them out, and in the equations, do we need to include the units, or do we just
My colleagues of the Association of Physics Teachers, they say, listen, you have to put the units there, and it's the right thing to do. I don't do it because I'm too sloppy when I write.
Yeah.
And then I get kilograms, and then I have a G, and then in physics 2A there is a G that is 9.8. It's a big confusion. So I don't put the units as I develop the equation.
Okay.
I put in the end always, and I ask you guys to do the same.
Okay.
No. Now it's pretty much up to you. And the reason for that is if you go and you learn physics in high school, you learn about units, right? So you know that force Newton is equal to mass times acceleration. So is kilogram times length divided by t squared, right? And sometimes you plug quantities in the wrong way, and then you ended up with the unit that's not the unit that you're supposed to have.
Yeah.
So in addition to do the calculations, if you have the units inserted, it helps to double check your development. So it is a good thing to do, but I don't do because I'm incapable. It's my limitation, all right? And too bad it's being taped. It goes viral. Oh, the teacher's doing what he's not supposed to. This is completely a lie. I do all the units. I put it there. I always do. No, I don't. You guys got it? Did it? Set that equation. Work is energy. So when you go to the store and you buy a battery of 1.5 volts or 3 of them because you want to have a system of 4 volts or 4.5 volts, whatever. Now you know what's going on. You are going to take that battery, and if you put in a circuit, you are going to allow every single electron that is connected in that circuit to have a certain amount of energy to do things. And the electrons will move. And as they move, they will take that energy that you're providing with battery, which is pretty much chemical energy. So the electron is going to take that and do things. It's going to warm up your toast, warm up your water, shower, and you name it. Okay, so that's the idea of that I would like you to have of this chapter 19 and what volts represent. It's the amount of energy that is stored in there, chemical energy, and when that is given to particles, they take that energy and move. And as they move, they collide, they do things. And the collision means heat, and that's why you have a temperature rise in toast, in water, and so on, so on, so on. So let's try to solve this one. So you have an electron here. An electron, sometimes, I don't know if it is in this problem. Sometimes it's important you realize and you keep your antenna on because electron has a negative charge, right? Negative 1.6 10 to minus 19 coulomb. And because of this negative charge, once it is in the field, it's going to move in the direction opposite to the field, right? When we learn circuit, this is the definition of a battery or a power supply, positive and negative end. You saw that in the lab, and you have some appliance here, some light bulb or something. So once you close the circuit, like is given in this symbol, electrons will rush from the negative end. This is the real electronic current. Electronic current. Electronic current. So electrons will rush from the negative end, and as in fact, they don't rush with high speed. In fact, they go very low speed because they collide here and there with the nucleons in the metal or copper, whatever that is, and the net motion of these electrons is very, very small. But the electric field is instantaneous, right? Once speed of light. Once you close the circuit, everybody starts trying to move slowly, but it's enough to provide energy and energy being dissipated. Now, electrons go from the negative end to the positive end. The electric field, the vector electric field, has an orientation from positive to negative. Like in a positive charge, if you have a positive charge, the electric field, the lines are radially given out of the positive charge. So go from positive to the negative charge. So if you have a dipole configuration, like you guys did see in the lab, the field lines go from positive to negative, right? Positive to negative. And that's the direction of the field. So if you put an electron here, electron will rush in the opposite direction because it has a negative charge. So just pay attention to that. So you have a potential difference of 1500 volts. So we write that down as a given information. And we want to find the speed. The charge is given, and the mass of the electron is also given, right? So we have a mass of the electron. So how can we find the speed? Now, this is a two-level sort of a problem. So the first level is physics 2B, and that requires that you remember the definition of volts, which is energy per unit of charge, energy that is given to the circuit per unit of charge. So an energy then can be figured here, right? So you know the charge of electron, and I can drop now the negative because I know this is not going to be too much important. We want to find the speed. The speed is a scalar. So 1.6 10 to minus 19 times the voltage, which is 1500 joules of energy. So we basically have, this is wrong. What am I doing here? How come no one shouted? 1500, see how important it is to put the units. Now you know. I said 1500 joules is equal joules. That something is wrong. Okay. Volts. So, and this is Coulomb. Okay. So now we have the work, and we have to calculate this. Did somebody calculate? 1.4 2.4 10 to
power
minus 16. So joules, the unit of energy. Now, how do we relate energy to speed? Well, we know this energy transferred to electron is used by the electron to gain speed, to gain kinetic energy, and assuming the kinetic energy initial is zero, right? Work is equal to change in kinetic energy, final kinetic energy, minus initial kinetic energy, which we assume the electron was at rest. So the initial speed was zero. Okay, so this is zero. So basically we can find now our final speed, which is going to be 2 times 2.4 times 10 to minus 16. I'm operating the math in the line above, divided by the mass of the electron, which is given 9.11 10 to minus 31 kilogram. And once I take a square root of both sides, I can figure my speed in meters per second. Okay? Good enough? You guys are not saying anything. Ah, thank you. Thank you, sir.
Could you go back up?
Yes, I can. Where do you want me to go?
Higher.
Yeah. What?
That's why we're quiet.
What?
Taping's dangerous.
Dangerous.
Scary.
What happened?
Because you're recording.
Oh, yeah. Oh, because, yeah.
I don't want to embarrass myself.
Oh, no. Besides, I'm pretty sure when you go and review the tapes, you're not going to be able to hear you.
Okay,
Yeah.
yeah.
Then you lower the volume in your computer.
Then watch the video.
Thomas, is that all right?
So what did you do? What's the second part of the problem? I got the first part. The second part.
Oh, the second part, yes. So in the first part, you got the energy, right?
Yeah.
And the energy is a number 2.4 10 to minus 16 joules. But the energy, we learn in physics 2A, is the change in kinetic energy. Work is equal to change in kinetic energy. And that's why this goes delta change in kinetic energy. Now, change in kinetic energy, there is an expression for kinetic energy, half mv squared final minus the initial one.
In this type of question, we assume all the energy transfers to kinetic energy. There is no resistance. There is no.
That is a very good point. Yes, in this case,
An ideal
in ideal situation, see in the first problem, see, without friction, see that? There is no friction there. So in ideal situation, you have this electron kind of afloat in the space. There is no resistance. So electric field gives the electric force, which is the only force on the particle. And that's the only one. Now, in real situation, if you have electrons in a circuit, you have a heck of a resistance. First of all, you have the resistors. So you have your appliance, your hot tub, and everything. Second, the cables itself, the copper cables, the nucleons try to hold the electrons. So the electrons, they move, but they bounce back, and they keep going with a speed that's called drift velocity, which is very small. It's centimeters per second, if I'm not mistaken. It is a very small speed. Tom, is that right?
I mean, I'm good up to now, but like, what? You don't have an initial velocity, do you?
We do. In the previous problem, you have 55. So if I am an evil person, right, in the exam, I ask you what is the final speed. Knowing the initial speed was 55, you cannot put 0 as the initial speed. You would have to go on your equation here, and I'll put it in circle so you don't make confusion. You would put 55 there, because that was the initial. So the speed would be increased. During the process, you have a voltage applied to the particle.
So for this problem, you basically plug in 0 for that and divide that by the kinetic energy.
Oh, okay. So let's go to this problem now. So you put a 0 here. So you have half mass of the electron, which is 9.1 10 to minus 31. I mean the first term times final velocity square, which I don't know, minus half mass of electron, which is 9.1 something, times 0 square. Now this is 0. 0 multiplied by mass divided by 2 is 0. So I'm left with 2.5 10 to minus 16 joules, which is this term here, right, is equal to the change in kinetic energy, which is this term here, half 9.1 10 to minus 31 V final square. Okay? And then I can multiply per 2 and divide by 9.1 10 to minus 31 in both sides of the equations. So when I do that, yeah, I have a VF alone in the right-hand side of the equation. And I have this math here that I have to solve. So what I do next, I have VF squared, and I have this number. This number must be calculated. Did somebody calculate that? Did you calculate that?
It's 2.3.
The square?
No, the square is. I have to, it's 5.3 10 to power 14.
10 to 14?
Yeah.
Okay. Meters per square second. Meter squared per square second. So, and then what we do next, we take square root of both sides, and then we can solve the problem. Oh, plus 14. Okay? Um, 4 is the same thing you do tomorrow night before going dancing. Okay, how about this? How about this? Is this problems, at least the development you should do, is in any way different from what we've done so far?
So just like work called QV, and then we have work,
We have the work. So because we have the Jews, I mean, when you read this problem, it has 50 Jews. You have to know that Joules is a unit that is energy, right? That's the work. So then you start kind of solving the problem that apparently is complicated, but now you know what it is. So and the person who wrote was nice. They say 50 joules of energy. You could say if it takes 50 joules to move, so it was energy. Okay, energy, right? So you have energy, which is 50 joules, and we have a charge given 10 coulombs from point A to point B. So you want to move the charge that way. What is the magnitude of potential difference? So what is potential difference? Which letter represents potential difference between 2 points? V. So we want to find VAB, right? We want to find V. This is what we want to look for. And then you have to remember, okay, I think V, I know what it is the amount of energy that is dispersed or transferred to this charge, so the charge can be accelerated somehow, divided by its unit of charge, and then you can get your problem solved. Okay? Got it? Elizabeth seems so driven into your book. Is that okay? All right. See, this is the same thing. Same thing. You can do not Friday night, but do Saturday night before you go into the bar. Just to get in the mood. Okay. Now, this is a problem with circuits. Oh, by the way, if you have any homework problem that is affliging you, we can take some time and go over that. Okay? I think we have some extra time going. It's funny, using this approach, I thought I would not have enough time to cover 10 problems, and I'm done. Almost. So it seems to be efficient. Or you guys are too quiet. Whatever works, it works. All right, so number 7. End of class, we define capacitors. And next week class, you guys are going to do a lab with capacitor. It's a 1 Faraday capacitor, and you're going to see the capacitor discharging and doing things in the circuit. It's going to be a nice introduction, I think. And since this capacitor has the power or the ability of accumulating so much charge, instead of using the power supply, I'm going to use batteries, because then I can guarantee the current's going to be low there. If somebody make a mistake and put 500 volts there, that's not going to be good. Okay, so capacitors, what they do in the circuits, they drain charge and they accumulate charge in there. So if the capacitor is not charged, and then you put in the circuit, and then you turn on the circuit, so initially this capacitor will start draining energy because it didn't have charge. It's going to start accumulating like a squirrel. It's going to take all these nuts and put it somewhere. So that's what capacitors do when it's not charged. So eventually the capacitor is going to be charged. So when the capacitor is charged, it's not going to drain current anymore to it. Which means if you have a branch in a circuit that has a capacitor that is all charged, there will be no current going on there because it doesn't need it. Okay? But then you elaborate a circuit so that when the circuit needs some extra surplus of energy, you use the capacitor to provide that. And then you build a circuit that way. So a switch is open, now the capacitor discharge, and then you have this current drain to do something. And then you can do your circuit or build a circuit in such a way that you have this on off, like in a blinker. So you're gonna turn left, turn right, and then you have a capacitor doing this nice, tricky thing, blinking the lights on and off, on and off. We have also one lab that can that use an LED for that purposes. Okay, so and then you have a blinking circuit. We might play with that one as well because it's cool. Now, sometimes so basically you go to the store and then you buy a capacitor that has what is called capacitance. So capacitance is a quantity that is given by the amount of charge the capacitor can accumulate divided by its voltage, which means the voltage across its terminals, okay, or its plates. And so you have basically a charge and you have a voltage in there. And that is the definition of capacitance. Now, capacitance is physically given to
alert from system UI server
to the instrument. Low battery. So this is physically, this is intrinsically part of the capacitor. So capacitance does not depend on charge or voltage specifically. So if you give a certain voltage, the capacitor will store a certain amount of charge. If you increase the voltage, you might affect the charge distribution too. So you increase the voltage, you increase the charge. That's why I was mentioned, if I go with a capacitor that has a large capacitance, if you put a 500 volts there, you're gonna have a heck of a charge, and that thing might start sparking like a, yeah. So we don't want that. So we have to be careful. But anyways, sometimes you don't have the capacitor with the characteristics you have, but you have several other types of capacitors. So what you do arrangement of capacitors. And then the arrangement is one that is in series, like this, or one that is so-called parallel. So current is flowing down, you have a splitting current going right and left. So the basic definition between branches of a circuit that happen to be parallel and branches of a circuit that are called to be in series is that in a series branch, the current is unique. So these two capacitors are in series if the current that goes through them is the same. It's not a different one, right? So certainly, if you have a current I know to the right, I1 to the left, the currents are not the same, so it is said these two capacitors are in parallel. The currents are not the same. But the definition of parallel branch is one that the voltage difference across the capacitors end is the same. So this branch here is parallel to this branch because the voltage across the two capacitors plate is basically the same, right? There is no difference. And here is in series because the current is the same. So a group of capacitors are in series if current across is the same. Now, if they are in parallel, the voltage, uh, the voltage is the same. So once you identify in your circuit which ones are in series and which one happen to be in parallel, the next thing you do is to replace this group by what is called equivalent capacitor. So an equivalent capacitor of a group of capacitors in series is one in which the charge is the same. So capacitors in series, they have the same charge, although their voltage happen to be different. This is important. So the charges are the same, the voltages are different. And when you get an equivalent capacitor that has what's called equivalent capacitance, the voltage across their terminal or its terminal is given by adding up those three voltages. V1, V2, and V3 summing. Now, if you have a situation in which the three capacitors are in parallel, you can also think about an equivalent capacitor. And the voltage here is the same as here. The voltage is the same. In series, the charge is the same. In parallel, the voltage is the same. Why Siri is stopping me?
I found something on the web about the chargers.
I didn't ask you for anything. And my son got Alexa. It's so weird. It's so weird. Who has Alexa in the house? You have Alexa, and you have Alexa. Don't you think it's weird?
I know my brother uses it, but
It's kind of weird. Alexa, turn off the light.
maybe it's one.
Yeah, all kinds of turn on TV. And what is weird is I'm talking to him, and Alexa, no. This is weird, you know. It's really weird. And I'm taping that. Oh yeah. So, but the equivalent is voltage is the same, but look at this. The charge now, the equivalent charge is equal by the sum of the previous charge. It's kind of a okay, because if you think about charge as being energy, kind of, right? Or if you have a lot of charge, you have a lot of energy accumulated because of voltage. So charge cannot disappear. So if you take this group of charge, right, a bunch of extra electrons, and squeeze them into one capacitor, they have to be there, right? They don't go away, they don't disappear. So the final charge is given by summing up the charge of each of that was in each of the capacitors, and the voltage across is the same. Yes. Yeah, the voltage here is going to be given by the sum of the voltage. The Q is the same. This Q here is the same. The charge in the equivalent capacitor in series has to be the same. Has to be the same. And the voltage is not. Here, the final charge is given by the sum of each one of the charge because the charges are not the same. Q2 and Q3. Okay? Now you are sitting in your chair and think, okay, what do I need to know of this stuff? Well, what you need to know is if I give you a circuit, you have to tell me what is the final voltage in a circuit. That's the exercise in there. Okay. So how do we solve for this type of problem? So let's see if we can do that. Now, as you can see in this circuit here, the voltage, I don't know what is being asked. Let me see. A network of capacitors connect across a potential difference V naught. So this is V naught. What should V naught be so that 60 microfarad capacitor will have that much coulomb of charge on each of its plates? Oh, this one. Okay, so let's do one thing at a time. Let's do everything in this circuit. Let's calculate everything, all the voltage, all the charges, everything. But before we do that, since is the first time we are solving this type of problem, when you look at a circuit like this that has a combination of capacitors, here's my question. Are there any capacitor in this circuit that happen to be in series? Yes, where? Which capacitors are in series?
30, and then the combination of these two, and the 60.
The combination.
Yeah. Not only one, the combination.
Okay, that's correct. So you have this is in series with this, obvious, because the current that comes over here goes, has this capacitor in it. I don't want to say goes through the capacitor because the current doesn't pass through the capacitor, but just a way of saying. So the current goes through this capacitor, through this 1, 2, and the combination of those two. Okay. Are there any example of capacitor in parallel? So those two are in parallel. So the first thing you do in a circuit like this is say, okay, I have identified capacitors in series, capacitor in parallel, first of all. Second, you should be able to remember. If you don't remember, it's not a big deal because you will have your cheat sheet with you. In series, the equivalent capacitance is given by the inverse sum of each of the components. Okay. And in parallel, the equivalent capacitance is given by the sum of its components. Okay? So you have that in your cheat sheet. You just need to remember how to operate these things. So let's start with these two fellow over here. So they are in parallel, right? And I will redesign this circuit like this. And I will write in red to the node the equivalent capacitance of those two fellows in parallel. So how do I figure that out? How do I know the equivalent capacitance of them? There are ways of carrying notation. Some students like to write like this, or some others they prefer to write C, and then you write 20, 10, right? So 20 and 10, or if 4, 5, 6, 4, 5, 6. So they just write, which can be, you know, kind of a heavy. Whatever you want to do, just make sure you are organized on that. So I'm going to write equivalent. So the equivalent capacitance here is what? So it's in parallel. The equivalent capacitance of two capacitors in parallel is given by the sum of them. And the sum is 30. Okay. Now I found myself with, as Yahya said, I have now two capacitors in series, and the combination is also in series. And then I can solve using the equation of the inverse sum of them. So this is my V naught, and now what I have is this. Now 1 over Cx prime is equal 1 over 30 plus 1 over 30 plus 1 over 60. And that is equal to So when I get to this point, what I should not forget is to do what? What shouldn't I forget? To flip it over, right? Because I want the equivalent capacitance, and that is 12 microfarad. It's not 1 over 12. So don't forget, you go all the way to the end and then you flip, right? If you don't flip, you're not doing right. Okay, this is the equivalent capacitance of the entire circuit, which is, yes?
Why do you flip it?
Because you have 1 over the equivalent capacitance is equal 1 over 12. So I don't want a 1 over the equivalent. I want the equivalent. So I cross multiply those terms. So when I cross multiply, 12 microfarad comes to the left, and the equivalent capacitance goes to the right. Okay. Okay. So what should be V naught so that this capacitor will have this much coulomb of charge on each of these plates? So it is saying this 6 microfarad has 18 microcoulomb. So why this information helps me? I mean, in what this information helps me to solve this problem? You have to remember one of the concepts of capacitors in series, and that is what? The voltage is not the same. So, I put it right here. So here's the charge of this 6 microfarad capacitor, right?
Who would have 18?
Is given. What should V naught be so that this capacitor has this much charge on its plate? So what we want to find, what we want to solve for, we want to solve for V naught. This is what we want to solve for. So we want to solve for V naught. This is what we want to find. We develop to the point that we have one equivalent capacitor that we know what is its capacitance is, right? We know this. So we want to find V naught. So what properties of capacitors can we use that will help us to solve this problem? If the per capacitor has a charge of 18 microcoulomb, all the others have the same charge. Not only that, the equivalent capacitor has the same charge. Got it? So basically, if this is 18 microcoulomb charge, this is also 18 microcoulomb charge, this is also 18 microcoulomb charge, and this is also 18 microcoulomb charge. Are we all there? Can we find V naught now? So now, look at this. The circuit is one that I have a capacitor with a capacitance that is 12 microfarad. It has a charge of 18 microcoulomb. And I want to find V naught. How do I do this? I use the definition of capacitance. Capacitance is Q over V. So therefore, V is equal Q over C. So the voltage shall be, or V naught in this case, so we are talking about V naught will be 18 microcoulomb divided by 12 microfarad. And then we do this definition, we have our V naught in units of volts. Okay? All good there? B, under the conditions of part A, how much total energy is stored in this network of capacitors? Well, I didn't cover that yet. Since I don't cover it, don't need to worry about it. But the energy is equal by half CV squared. It's an equation. Okay?
Also, I understood where the charge came from, the 18, but where did you pull the 12 ground from?
The 12 is the capacitance which we calculated in the previous step.
Okay,
Is the equivalent capacitance of this group of capacitors. Okay? All good? So energy is half CV squared. There are different options for energy equation. You can also write, since C is Q over V, you can also write this energy as half QV, and just plug the numbers and you should have it. How about this?
Could you go up?
Yes.
Oh, could you go up?
Oh, yes, I can go up. I forgot to mention, those of you who got late, I'm taping this, and I'm taking all of this and putting in Canvas. So by the afternoon, you could review all of that. Yes?
So I know you're looking for the 18 microfarads on the last capacitor there, but how do you know that there's 18 on each one of them?
Because that is the property of capacitors in series.
Okay.
The charge in each one of their plates must be the same. So So the idea is, if this is a charge that is bigger than that one, it's gonna be transferred to the other one.
Okay. And then
They
once
have
you
to be in equilibrium.
and once you combine the parallel, it's basically
In parallel, the charge
right.
can be different.
Right, I'm good with that. I'm just saying in this particular problem, you had one that wasn't parallel, but once you combine it,
Becoming parallel.
Once you combine it, it's basically a series.
Yes. In fact, this is a good point. Let me go back to where we were right there. So the charge in these capacitors are not the same. But when you add those two charges, you gotta have 18 microcoulomb. Okay. I don't have time to do much, or do. I'm taking that. So let me see if it's gonna take too long because I know you guys have things to do. I could outline. So we have a network of capacitors inside a sealed box. So this is a box. But one capacitor, CX, where is CX? This one, is sticking out, as shown in the figure. When you connect the multimeter across points A and B, it reads 27 microfarad. So what is CX? What is CX? So how do you figure that? What? Yeah, it means that you can go with a multimeter like the device we had in the lab this week, and then you can plug it in there, and then you can read the capacitance. It's outside so you can read it. If it's inside the box, you cannot go in there.
But they're still in parallel, right?
It's in parallel, yeah. So exactly what you're reading, when you put your multimeter here, you are not reading the capacitance of this capacitor. What are you reading? The equivalence of all these different capacitors in parallel. They are in parallel, right? So the solution is quick. If they are in parallel, CX plus 10
plus 5 plus
10 plus what?
5
Plus what?
8.
8 is equal to 27. And then you can figure your. Got it? Looks like complicated, right? But when you bring the concepts in perspective,
Should be 23.
and should be no less.
10 plus
15,
5.
23. Oh yeah, it should be 4 microfarad. So CX should be 4 microfarad. All good? Does anybody want to say something to the world? All right. Okay, have a nice. Whatever is in the syllabus. I don't know what is in the syllabus now. I will check it and I'll let you know. But on Monday there is no class. Don't forget that. Don't come here because you're not gonna find anyone. I will not be here, that's for sure.
Well, we don't have class anyways on Monday.
No class on Monday.
How
Yeah.
do we do it? How do we turn in the homework? So we just take a picture and send it to the email.
Yeah, you upload in Canvas.
Oh, in Canvas?
Yeah.
Check it out.
Yeah, I prefer that way instead of a paper version. But if you bring paper version, is okay.
Oh, yeah.
But when you upload, make sure it is straight up.
Okay, lie up.
Yeah, if it's all tilted, it's
Hi.
yeah.
Thank you.
Preston, do you have office hours right now?
I have, yeah, I don't, but I can have it.
want to ask one question about